We're discussing logarithm of a quotient property and its matching theorem. This is 12.4c. We've got 10 previous videos for chapter 12 now that are linked in this description. So, just as with exponential functions, the base of a log function has to be positive. So here's our theorem, our property. It's the log of a quotient for any positive number x, y, and that base a is greater than 0 and it doesn't equal a 1. Log base a of the quotient of x and y is going to equal its difference, log base a of x minus log base a of y. Logarithmic functions share similar properties with their exponential counterparts. When needed, the properties of logarithms allow us to manipulate log expressions so we can solve equations or simplify terms. So let me show you this up here. This is how it's like its exponential counterparts. We've got log base a of the quotient of x and y, and it equals log base a of x minus log base a of y. Remember, logs are exponents, and it's equivalent to the quotient of a to the x and a to the y. Remember, when the base is the same, we just subtract the exponents. Remember that? So that's why we're doing this. That's why we're subtracting here, okay? And this theorem says that the logarithm of a quotient is the logarithm of the dividend minus the logarithm of the divisor. Dividend, divisor. Now, you have to be careful. If you see something like this, where we've got the quotient of the log of x and the log of y, it does not equal this. If we put in some real numbers, log base 2 of 8 is a 3, and log base 2 of 4 is a 2. If we do 8 minus 4, we're going to get a 4. Log base 2 of 4 is a 2. And 3 divided by 2 is not equal to 2, is it? It's 1.5. So be careful. We're going to talk about this more at the end of the video, okay? So we can express logs as a difference. If you see log base a of the quotient of m and n, we write it as a difference. If you see log base c of 1/4, well, a fraction is a little division problem, isn't it? So we've got log base c of 1 minus log base c of 4. We can express them as sums and differences of logs and without exponential notation or radicals. We have log base 10 of the quotient of 4 pi and the square root of 23. That's going to equal log base 10 of 4 plus log base 10 of pi, because these are being multiplied together, right? And we did log of a product in video 12.4a. It's the sum of the addends. That's the log of a product. And for this square root of 23, we know that there's a little invisible index 2 there, right? When we write square roots, they just don't write the little index 2. And that's the denominator of a rational exponent. So this square root of 23 is equal to 23 to the half. If you're confused about this, there's links to 7.5b and 7.5c where we talked about rational exponents, all right? So now, because we've got this division problem, we can do this minus this, can't we? And if this is 23 to the half, that means we have half times log base 10 of 23. All right? Stay with me. We can express in terms of logarithms, x, y, and z. So now we've got log base a of the square of the quotient of z cubed and xy. So we can remove this square root symbol and put it in parentheses with a little half exponent, right? Because of that little 2 that's not written here, that little index that I talked about, okay? So that makes it to the half exponent. Well, using the log of a power theorem that we talked about in 12.4b, that means we've got half times the log of the quotient of z cubed and xy. Using the log of a quotient, we're going to subtract, aren't we? So now we've got half times the log base a of z cubed minus the log base a of xy. Now we have to break this up, okay? And we can say it's half times log base a z cubed minus log base a of x minus log base a of y. And we're using both theorems there and the product one, okay? And when we distribute this half into the brackets, we're going to get 3/2 log base a of z minus half log base a of x minus half log base a of y. All right? Let's try that one again. That sounds really confusing, doesn't it? So we're going to express in terms of logarithms x, y, and z. So now we've got an index of 4 here, all right? So we've got log base a of this, we've got this little index 4, so we know that that's going to be a 1/4, right? Just like when we had the little 2 here, it became a half. So now we know that that little index is going to be a 1/4. When we remove this radical sign, we can put it in parentheses. So now using the log of a power theorem, which was 12.4b, we've got 1/4 times log base a of the quotient of x, y, and z cubed. That's going to be 1/4 distributed to log base a of the product of x and y, which we can break up as addends, right? And this z cubed. So now we've got this. This is the log of the product theorem right here that we opened up as the sum of the addends. We can distribute this 1/4. We're using both the log of a power and log of a quotient theorems here. Log of a product and log of a quotient theorem here, okay? Because it's going to be subtraction, but we had this multiplication, didn't we, that we had to break up into addends, all right? And we get 1/4 times log base a of x plus 1/4 times log base a of y minus 3/4. See, because the 1/4 times that cube, log base a of z, all right? We can express it as a difference. So looking at this, if we were to plug in the numbers 8 and 4 for x and y, we have log base 2 of the quotient of 8 and 4. Remember, a logarithm is an exponent, and we subtract exponents when dividing. So this would be 2 x to the third, wouldn't it? Because we subtract the exponents. We divide the 6 and 3, the coefficients, but then the base here are the same. So we're going to do 5 minus 2, so that would be 2x cubed, wouldn't it? So you have to remember that logs are exponents and keep thinking of them that way, all right? So this is going to be log base 2 of 8 minus log base 2 of 4. Well, 2 to the what power equals 8? 3. 2 to the what power equals 4? 2. We've got 3 minus 2, which is a 1. So that's a 1, see? Now, we can express as a single logarithm. We can go backwards from what we did with the x, y, z. So if we had this, we made it into this, didn't we? Now we can go from this back to a single logarithm. So if you see half times log base a of x minus 7 times log base a of y, we know that that's going to be division, isn't it? This part of it right here is division. We also know that if you see this half, that it's x squared, because there's that little 2 index there, right? This is the exponent for y, that's 7, see? And because it's subtraction, we can write it as quotients like this. We've got plus log base a of z. Well, that's an addend, isn't it? So that means we're going to multiply this to that square of x. See how I got that? Let me back up a little bit so you can see. We're basically just doing the reverse of what we did before, all right? Now, given that log base a of 2 is approximately 0.301, that's what it's given. We're assigning that for this problem. And let's say that log base a of 3 is approximately 0.477. if they want us to find the quotient of log base a of 2 and log base a of 3, well, that's a to the what power equals 2? That's what it's asking, isn't it? And it's saying 0.301. And this is saying a to the what power equals 3, isn't it? Well, it tells us 0.477. That means we've got 0.301 divided by 0.477. And none of those properties that we've talked about in the last few videos are going to help us here. We just need to divide. We're going to get approximately 0.63. And it was 1 something something something, so I rounded it to 0.63. All right? So now, be really, really careful. And this is what I was talking about before when you see them on top of each other, okay? Just need to divide, all right? So now, if it says something like find log base a of 5, and it told us, it gave us these values, you can't add this 2 and this 3 to get that 5 from this given information. You cannot find log base a of 5. Log base a of 2 plus log base a of 3 does not equal log base a of 5. All right? So let's plug in some real numbers. Well, we know that 16 equals 8 plus 8, right? So let's try that. 2 to the what power is 16? 2 to the 4th power, so that's a 4. 2 to the what power is 8? 3. So that's a 3, which means that's a 3, and 4 is not equal to 3 plus 3. So see how we can't just add this 2 and 3 and get that 5? All right. So we've talked about these properties. We talked about equivalence in 12.3a. We talked about log of a product in 12.4a. We talked about log of a power in 12.4b, and now we've talked about log of a quotient. All right? Next video, we're going to talk about log of 1 and log of the base, all right? That'll be 12.4D. I'm going to add this video to the Algebra 2 playlist, and there's going to be those 10 previous videos for Chapter 12 linked in the description, and there's going to be links to 7.5 A, B, C, and D, where we talked about rational exponents, all right? So, I hope this was helpful. This is very complex for some people, but I've been trying to break it into as little parts as I can and go as slow as I can so that you can understand, all right? Just remember, a logarithm is an exponent. Just keep remembering to treat it that way, all right? I'll see you next video. Bye.